Alright, this is what we did on Wednesday and Thursday, block day, October 3rd and 4th. We start out talking about light and electrons. Light is produced when electrons are excited. The second picture on this worksheet shows us an electron in the ground state, and energy's coming in. As the energy comes in, the electron gets excited and it jumps to a higher energy level. It has more energy, so it can move out. Then it falls back when it releases the energy, and that energy is released as a photon of light. And we're back to the ground state. Okay, so if you want to write a few words and kind of paraphrase what I just told you here, you can, but that's what we're doing. That's what question number 2 is about. Back to question number 1. We talked about all the different types of light. We know that the longest wavelength of light is radio. And then we have microwave, infrared, visible, ultraviolet, my brain's not working this early in the morning, X-ray, and gamma radiation. And you can see with the picture drawn here that as we go from left to right, if we line them up this way, the wavelength, which is the length from here to here, is getting smaller. So the wavelength's getting smaller, that means it's waving back and forth more, so its frequency is increasing. So our frequency increases this way, and our wavelength increases going the other way. And that's going to be important here in a moment. Now, we just talked about the electron. The energy that hits the electron we call a quanta of energy. The energy will not land if the energy won't land the electron on a specific energy level, the electron doesn't go. It can't, if it takes 20 joules of energy for it to jump from one energy level to the next and it only gets 18, it's not going to jump halfway. It's not going to go. It'll just stay there. All right. Depending on what element you have and how far the electrons are going, you're going to get different light emitted. And that's what we call these emission spectra. That's what we looked at with the rainbow glasses. The emission spectra is indicating different electrons that are jumping. Those are photons that are being produced by electrons. Now, there's also something called an absorption spectra. We were looking at electrons that were excited, and they passed through a prism, which was the glasses, so we could see the emission spectra. But if we look through the spectrum at light that's passing through a gas, instead that will actually excite the gas, and the gas will, the atoms, the electrons will eat that energy out of they'll pick up that particular wavelength of energy as it comes through, and we get this instead. We get an absorption spectra, which is like a negative of the emission spectra. Okay, so that's the difference between an absorption and an emission spectra. All right, now we're going to talk about. I didn't get an extra page here. Hang on. All right, good. Now I've got more space. Okay. So we talked about that relationship between frequency and wavelength. As wavelength increases, frequency decreases. We use this symbol, which is the Greek letter lambda, the lowercase lambda, for wavelength. And we use this symbol, which is the Greek letter nu, for frequency. And they vary inversely. As one goes up, the other goes down. Mathematically speaking, if you multiply two variables that are inverse, you will end up with a constant. So if we multiply wavelength times frequency, we end up with a constant, and that constant happens to be the speed of light, which is 3.0 times 10 to the 8th meters per second. That speed of light, all light travels at that speed in a vacuum. So radio waves travel at the speed of 3 times 10 to the 8th meters per second. That's 300 million meters per second. Gamma rays travel at that same speed. They all travel at the same speed. Because that's true, if we know the wavelength of something, we can calculate its frequency and vice versa. And that's what this first part at the top of the worksheet is about. Here we have the electromagnetic spectra. Here's the speed of light. And it shows us that speed is equal to frequency times wavelength. And I'm going to make a little thing. They've used a cute little circle, but I'm going to use a triangle. And it kind of looks like the Deathly Hallows, if you're a Harry Potter fan. And what we're going to do, if we put the constant into the top, and we put frequency times wavelength down here, we end up with a way to convert our equation around. All right, C is equal to frequency times wavelength. If we are going to solve for wavelength, and we cover wavelength up, you see what we have to do. Wavelength is equal to the speed of light divided by frequency. Try and take that away. Now, if we want to solve for frequency, it's the speed of light divided by wavelength. So now we're going to work these problems. The first question says violet light has a wavelength of 4.10 times 10 to the negative 12th meters. What is the frequency? So we're going to solve for frequency, which is what I have covered up right here. Frequency is equal to the speed of light divided by wavelength. So we're going to take the speed of light, 3.0 times 10 to the 8th meters per second, and we'll divide it by frequency. Wavelength. Okay, so let me find a calculator. He's going to have to teach me how to use this surface calculator. So we'll take the speed of light, 3.0 times 10 to the 8th, divided by, good morning, our wavelength, 4.10 times 10 to the negative 12th. And if we count up our zero, or if we move our decimal, count our decimal places, we go 3, 6, 9, 12, 15, 18, we would have an answer that would be 7.31 times 10 to the 19th. Now, bear with me while I figure out how to get rid of the calculator. And I've already forgotten what the answer was. And the units are 1 over seconds. The second one, we're going to take speed of light. Speed of light, 3.0 times 10 to the 8th meters per second, divided by our frequency, 6.01 times 10 to the 14th. 1 over seconds is the same as a hertz. So I'm going to do that on my calculator here in front of me, not on the calculator on the computer because it's just easier on me. 3 times 10 to the 8th divided by 6.01 times 10 to the 14th, and we get 4.9 times 10 to the negative 7th. Meters. Okay. Number 3, we're going to take, first we have to convert kilohertz to regular hertz. There are 640 kilohertz, and we know that there are 1,000 hertz and 1 kilohertz. So we're going to multiply 640 times 1,000. So our frequency is going to end up being 640,000 hertz. So we'll take the speed of light divided by 640,000 hertz, which is 1 over seconds, and we will get 468 meters, which is the size of roughly 5 football fields. The last one, calculate the wavelength of radiation with a frequency of 8 times 10 to the 14th. So again, 3.0 times 10 to the 8th divided by 8.0 times 10 to the 14th will give us 3.75 times 10 to the negative 7th meters. All right, so that relationship is an inverse relationship. The relationship between energy and frequency is a direct relationship. So if we multiply an inverse relationship to get a constant, in order to get a constant with a direct relationship, you divide. Our constant we call h in this case, and that is equal to energy divided by frequency. H is also called Planck's constant, as Planck is kind of the guy that developed this whole thing about electrons and light and energy and all that. So, I can make my Deathly Hallows here, and you can see energy divided by Planck's constant will give us frequency if we hide that guy. And then energy divided by, if we want to calculate Planck's constant, we would take energy divided by frequency. And if we want to calculate energy, we multiply that. So the first question asks us to multiply. I'm run out of room again. Well, we'll just work with it. 8.5 times 10 to the 14th hertz, which is 1 over seconds, times Planck's constant, which is 6.63 times 10 to the negative 34th. When we do that math, 8.5 we get 5.64 times 10 to the negative 19th joules. All right, I'm going to stop there just because I'm running out of room. If you have additional questions, you can come in and see me at any time.